Okay, so welcome everyone. This is the problem solving session of the course Ring Theory NOC 24 MA 29. We are in the week 1. I am Pawan Kumar. So I will be solving some sample questions related to the theory that has been taught in the week that will help you to solve the current assignments and understand the concept better. Due to some technical reasons, my video camera is not on, my laptop's camera is not working. So sorry for that. So this will be more of a interactive session. So whenever I ask some questions, I'm expecting some nice response so that we can discuss and solve the problems, not the one-way teaching. It will be an interactive session. Okay. So let's start. So question number one. So let R denote the set of all functions from 0, 1 to R. Okay, this R is just the notation. This is the real. This is the set of all real numbers. So we know this is a ring, right? With a ring of real valued functions on 0, 1. Okay. Just a minute. So you are familiar with the concepts of subring, right? When is a subset of a ring a subring? This has to be closed under um, addition, subtraction, and multiplication, right? I mean, addition is enough. It has to be subgroup under addition, and then it has to be closed under multiplication. Okay. Now, will the question is, if this is your ring, then which of the following, this is the abbreviation for which of the following, are subrings of R? A is the set of all, I'll say that A, capital A, set of all functions which are in R such that f at q is 0 for every q in rationals of 0, 1. So will it be a subring? So question is, yeah, so what do we have to check? That f and g belongs to A is f minus g belongs to A and f g belongs to A, right? If I verify these two equations, then I can tell whether A is a subring or not. So let's see what happens for f minus g. So f minus g for any element q is, this is a component wise addition, hence f at q minus g at q, which is simply 0 minus 0, which is 0. And similarly, fg for any element q is the product. So fq times gq, which is also 0 since each term is 0, for all q belongs to rationals of 0, 1. Hence, A is a subring. So if you go further, you can ask whether this is an ideal, right? So what is an ideal? Ideal is a subring with one more extra property. So I'll write it here. Is this subring an ideal of R? So what is an ideal? You have an extra property that for any G belongs to R and F belongs to this set A, you need GF should belongs to A, right? That is true, right? You take any rational number Q, what is GF at Q? It is G at Q times F at Q, right? It doesn't matter what this G at Q is, you know this is 0. It implies the product is 0, which implies G belongs to A, right? So the answer is 2. This is also an ideal of R. Okay. Do you have any doubt? Anyone has any doubt? They can ask at any time. Okay. So for those who just joined, the first question is R is the ring of all functions on 0, 1 real valued functions. Then we are asking which of the following subsets of R is a subring. So the first subset was set of all functions which are 0 on rationals in 0, 1. Okay. So the answer is yes, this is a subring. Also, it is an ideal furthermore. Okay. So the second question is, in this question, the second part is, what if A is set of all polynomial functions? It is very easy to verify that for any polynomial, for any two polynomials, the sum is again a polynomial and the product is again a polynomial. So I'll leave this to you. Verify. The answer is yes. Verify. Then I'll go for the next part C. What about if A is your set of all functions such that f has 0 on only a finite set? See, what is another way of nicely writing this set? Right? I can write this set as f belongs to, not this one, I'm sorry, R, such that f inverse of 0. Right? What does this mean? Set of all points x for which fx is 0. This is precisely set of all zeros of f, right? Is finite. So all functions whose zero set is finite, we call this set as A. So question is this A a subring? Can anyone answer me? Yeah. I'm audible, right? Hello.
Yes, sir, audible.
Okay, okay. So can anyone tell me about this C, part C? Will it be okay? Yeah, thank you, Pratik. Will this set A be is a subring? So what do we have to check? The same thing. The f minus g should be in A for any f and g, and the product should be in A, right? To check for any f comma g in A, need f minus g should be in A and f g should be in A. Okay, the point wise product. So does it always hold? What are your intuitions? So can we find two functions f and g from 0, 1 to r such that 0 set of f is finite, 0 set of g is finite, but the 0 set of f plus g is infinite? Okay, so I'll give an example. You have to consider it, think properly how you can construct examples. Suppose I take f as f of x equals to x simply for any x in close 0, 1, right? And I'll define g something strange. G of x is x, okay, or I'll define this as 1 plus x when x is in some set. Okay, what do I call this set? X is equals to 1 by n for some natural number, right? And then for other points it is x, okay, or not just x. I'll just define 1. This is also fine, right? We are not talking about continuity or something. So g of x is 1 when x is 1 by n, and otherwise it's 0. Sorry, otherwise it's x. So what happens for f minus g? F minus g will be 1 by n minus 1 when x equals to 1 by n, and otherwise it is 0. So see, f and g both are 0 only on finite set. See, f is 0 only at point singleton 0, and g is also 0 only at point singleton 0, right? So both f and g belongs to A, but f minus g does not belong to A, right? F minus g is 0 on everywhere except for this 1 by n, right? So the set of all zeros of f minus g is infinite. So C is not a subring, A is a subring, B is a subring, C is not a subring. Is this clear, part C? Yes, you have any doubt? Ashok Lakshman, your mic is on. Okay, thank you, brother. Let's go to next one, which is D. D. Now, what about set of all functions? If A is set of all functions such that f inverse of 0 is infinite. So I'm now collecting all functions from close 0 1 to R whose set of all zeros is infinite. Of course, to be this subring, you have to take union with 0, okay? Because singleton 0 is not there, so it cannot be subring naturally. But you consider the set A with singleton 0, okay? Set of all functions whose 0 set is infinite along with the set 0. I mean, here 0 is already there, but still. So how about this set? Here can we define two functions f and g. Zero sets are infinite, but if you add or subtract those two, the zero set is no longer infinite, right? So let's see. I'll define f as f of x is 1 when x is rational and 0 when x is in irrationals, right? I'll define g as g of x is equals to 0 when x in rationals and 1 when x in irrationals, right? This kind of functions will occur very naturally everywhere in real analysis. So see, my f and g both are in A because the zero sets are infinite, right? What happens to f plus g? Yeah. So what happens to f plus g? F plus g of x equals to, if I take x is in rational, then I'll get gx is 0 but fx is 1. So this is 1. If I take x is in irrational, then I get fx is 0 but gx is 1. So this is 1. So f plus g is all 1, right? Which implies f plus g cannot belongs to A because its 0 set is empty. And what do we have? A condition on A. The 0 set has to be infinite, right? So this is no longer closed under addition itself. So it's no longer subgroup. So long away for subring. Right? D is also wrong. Then we go to the next set with E. E is set of all functions such that now you take the limit as x goes to 1, but your set is from 0, 1, so you have to approach it from left side. Of fx, it has to be 0. So now this set, is this set a subring? So a similar process, we take two elements f comma g belongs to A, and then what happens for f minus g? So if you take limit as x goes to 1 minus f minus g at x, this is same as limit as x going to 1 minus fx minus gx, right? And limit you can distribute, right? So limit as x goes to 1 minus fx minus limit as x going to 1 gx. Since each of those quantities are 0, hence the whole difference is 0, which implies f minus g belongs to a. What happens for the product? What is the limit as x goes to 1? So here also you can distribute. Okay. See, you can, if you have studied real analysis or any analysis topology, you can see if f and g both are the functions whose limit is 0 at point at 1, then the product also has the limit 0, right? You can prove it. So what did I do? Subtraction for any two element, their difference is also in A. For any two elements, their product is also in A. So this A is a subring. So you started with the ring R, which is a set of all functions, and you considered these three subsets, and you classified which is a subring, which are not a subring. So A, B, and E are subrings, but C and D are not subring. Okay. If you have any doubt in this question, you can ask. These are simple questions, so I assume there is no doubt. So let's go further. So next is question 2. So first thing is, this is the basic question. Just want to take a review of integral domains. So what is an integral domain? Can anyone define or tell me the definition of an integral domain? Yes. So for integral domain, first thing is we have a ring, commutative ring with unity, let's say. So when is it called an integral domain? So,
If it has no zero divisors.
yeah, if it has no zero divisors. Now what is a zero divisor?
Uh, Zero divisor. A non-empty non-zero element A is said to be zero divisor if there exists a non-zero element B such that AB is equal to 0.
Perfect, perfect, perfect. So now then this is a very simple question. If R is an integral domain, so how we define integral domain is a ring with no zero divisors, okay? So I hope you heard him and you have watched the lecture, so you know the definition. Let R be an integral domain and you have x squared equals to 1 for some x, then prove that x equals to plus minus 1. So in an integral domain, you have only these two choices for x. But if you go other than integral domains, you can have more than two solutions for the equation x squared equals to 1. So how do I prove this? I'm sorry for my voice. I have some cold. So x square equals to 1 implies I have x square minus 1 0. If I do a basic factorization, I get this. So since my R is an integral domain and you have a product of two elements which are 0, at least one of those has to be 0. So if x plus 1 equals to 0 implies x equals to 1, or you have x plus 1 equals to 0, which implies x equals to minus 1. So you are done. In any case, x is either plus 1 or minus 1. Okay. So next is I'll define what is a nilpotent element. An element x belongs to R is called nilpotent if there exists m belongs to natural number such that if you do the product m times x raised to m, you get the zero element. That's all. And this is the definition of a nilpotent element. Right? So now I have some questions. A. Show that if n is a power kb for some k natural numbers and a and b are integers, then ab bar, okay, this is an element of z upon nz, right, is nilpotent. Okay, what do we have to show? See, z upon nz is a ring, we know, which is isomorphic to zn, right? So each element you write as I'll give a description. So what is z upon nz? This is simply 0 bar, 1 bar, 2 bar, goes until n minus 1 bar. What does this bar represent? For example, I bar is the set I plus nz, right? This is a description of this set z upon nz bar, z upon nz. And what is zero element? Zero bar is simply the set nz, right? Like if I take any natural number k, let's say, let k belongs to natural number when is k plus nz equals to nz. This happens if and only if k is a multiple of n, if and only if n divides k. Right? I mean, k has to be a multiple of n, then only these sets are same. Okay? This is the description of g upon nz. So my question is, if a and b are integers such that a power kb for some integer k is equals to n, then I have to show that ab bar is an element, is a nilpotent element of g upon nz. Right? Okay, how do I show this? So I have to show AB is a nilpotent element, right? So what is AB bar? It is AB plus NZ, right? Just 1 minute. Yes. So my AB bar is AB plus NZ. What is AB squared? You know, it is AB plus, so I mean you squared this term and then do the NZ. So, but what is this? This is because A and B are from integer, they are commutative. So I can write this as A square B square plus NZ, right? So I'll do it k times, then I get here A power k, B power k plus NZ, right? Or what is this? I know A power k, B is n, right? The given information is n equals to A power k, B. So I get here n times B raised to k minus 1 plus NZ, right? So this is a number which is a multiple of n plus NZ. So you know this is NZ, right? But NZ is a zero element of the quotient space Z upon NZ, which implies AB bar is nilpotent, right? Because when you multiply it k times, you get to the zero element of your ring. So it is a nilpotent element, right? So AB bar is nilpotent. This is fine. Now this is a sufficient condition. When can you say an element is nilpotent, right? If you are interested in what are the nilpotent elements of Z upon NZ, you got one sufficient condition, right? But how can we characterize all the nilpotent elements in Z upon NZ? So this is your second part. So any integer a you take is an integer show that A bar, okay, belongs to Z upon NZ is an is a nilpotent element if and only if every prime divisor of P, sorry, every prime divisor of N is also a divisor of A. Okay. So how can we prove this? Anyone has any ideas or anyone want to try? Shall I give time? You can respond in the chat box also if you have some mic problems. This session is going to be like this. I'll propose some question and then maybe I want you to try for like I don't know maybe 1 or 2 minutes and then we'll discuss. If not, or if you cannot solve, then I'll give you a solution, something like this. Okay, I'll give you some solutions. Hint. I want to show that let's suppose A is nilpotent element. I mean A bar is nilpotent. So this means there exists a natural number. I'll call this k. So let's say such that A bar to the power k is the zero element, right? But what that means? This means A power k plus nz is equals to nz, right? And you know when this happens? This happens if and only if A power k, I mean, is a multiple of n, right? Now, if suppose let P is a prime divisor of n, then naturally P will divide n times L, which implies P will divide A power k. But since P is a prime and you have A power k, this should imply P will divide A, right? So you're done. You take any prime number which is a divisor of n, you should get P is a divisor of A also, right? So you have proved it one side. A is an nilpotent. If A bar is an nilpotent element, then every prime divisor of n is also a divisor of A. Now let's go the other way around. Let every prime divisor of n is also a divisor of A. Now I can write the prime factorization of n. Let's say it is p1 raised to what's some alpha 1, p2 raised to alpha 2. It goes until let's say pk raised to alpha k. This is my n. I can factorize any natural number into a product of prime numbers. Okay. Now since each pi also divides a, right? What do I have choice for a? A will also be p1 raised to some beta 1, p2 raised to some beta 2, because all these factors has to be there, right? pk raised to beta k. I mean, this bi's are greater or equal 1 into some m, right? Any m belongs to natural number. So if I this has to be a because each pi divides a. So this pH has to be there in the prime factorization, right? No, doesn't matter what this M is, but this is the least condition we get. Now what happens? Suppose each Bi is greater than is beta I greater than alpha I, then we directly get N divides A, right? This will imply A bar is nilpotent. I mean, in this two steps, this will imply A plus Nz is Nz, which will imply A bar is nilpotent. This will simply imply A bar is 0, right? But this is not this is not the case always, right? I mean, this beta is can be smaller also, right? In that case, if I keep doing a power some r, then I know what happens here. P1 raised to I get r1 beta 1, right? Then I get P2 raised to r2 beta 2 up to pk raised to rk beta k, and then here I get m power k, right? So I can choose some this r, I mean not this r1, I'm sorry, this these are only r. Okay, this is r b1 r b2 r, because I'm doing the exponent r to the whole product, so the exponent gets distributed in each term, right? So I can choose r belongs to a natural number such that r beta I is strictly greater than alpha I, right? For every I. Yeah, but then in that case, what do you get? N will divide a power r, right? Because here you will get p power, I mean this alpha is number greater than alpha I, so you get n divides a power alpha, right? But yeah, then this will imply a power r plus nz is same as nz, right? This will imply a r bar is 0. I mean ar ar whole a bar whole raised to r is 0, which implies a bar is nilpotent. Okay, I hope you understand this solution. Do you have any doubts? Yes? Okay, if no doubts, we can go forward. Next question. So the next question I have is C, which says if you consider the ring as set of all functions from a non-empty set X to F, where F is a field, okay, consider this as a ring. Now X is non-empty set. The information is X is a non-empty set. F is a field. So consider the ring this. Show that R has no nilpotent elements. Okay, how do you show this? Take any element and let's see what happens with the power. Okay, I mean no non-zero nilpotent elements. Zero is always a nilpotent element. So let F belongs to R So what is f power k at x for any x belongs to k? F power k at x is, and we know the product operation here on the set of all functions is the pointwise product, right? So I get fx whole power k, right? And if I equate it to 0, since fx is an element in field and field is an integral domain, so this should imply fx is 0. So this is happening for all x, right? For all x belongs to capital X, which implies f has to be identically 0, right? So if I started with f being an nilpotent element, then I get a natural number k such that f power k is identically 0, which means fx is 0 for all x belongs to k, which means f is identically 0, right? So the only nilpotent element is singleton 0. That is a 0 function. Okay. Okay, so next question, number 4. Question number 4. Let R be a ring. Let R be a commutative ring in particular. Commutative ring with unity. Then part A, show that okay, and X belongs to R, be a nilpotent element. Show that X is 0 or a 0 divisor. Okay, how do you show this? See, the given information is X is a nilpotent element, right? And let X is non-zero, because if X is 0, then we are done in the first case directly. Let X is non-zero, then I have to show that X is a 0 divisor, right? X is an important element which imply x power m equals to 0 for some x for some m in natural number, right? So I can write x into x power m minus 1 is 0, right? So okay, this m here has to be greater or equal to, right? Because if x is 1, then you have x equals to 0, but I started with x is non-zero, right? So m has to be greater or equal to, which implies m minus 1 is greater or equal to 1, right? Hence you have x times x raised to m minus 1 equals to 0. X is non-zero and x raised to m minus 1 also non-zero, right? I mean, this m is you take here is the least integer m for which x power m is 0. Then I can conclude that x power m minus 1 is non-zero. So you can write x and a non-zero integer, a non-zero element of the ring. Their product is 0, which implies x is 0 divisor, right? Simply, when do you call an element a zero divisor? If there exists another non-zero element, so that the product of these two elements is zero, right? I found a non-zero element x raised to m minus 1, right? That means any nilpotent element is either zero or a zero divisor. Okay. So now let's go to 2. Show that Rx is nilpotent for any R belongs to the ring, right? I mean, given that x was nilpotent, this is easy since you have a commutative ring. What happens for Rx power m? You get Rx times Rx times Rx, you go on. But since it is commutative, you can do this operation reverse here, also here, like this. So you get x raised to m times x raised to m. Since x raised to m is 0, this is 0, which implies Rx is nilpotent. So part C is show that 1 plus x is a unit. So what is a unit? An element which has a multiplicative inverse. Okay. So how do I show that 1 plus x is a unit? One way is to explicitly give the inverse, right? If I can find, okay, so one way is if you find element v belongs to R such that 1 plus x times v is 1, then done, right? Okay, so let's find that element v. Uh, yeah. So what about you take v as first thing is x is nilpotent, so let's say x power m is 0, right? And the m is a natural number. So let's take v to be 1 minus x plus x squared minus x cubed, something like this. It will go until the last element will be something like plus minus x raised to m minus 1, let's say. It depends on even and odd, no, whether m is even or m is odd, the plus minus. Okay. So now what happens if I do 1 plus x times v, right? So I get first of all 1 times v is the v as it is, 1 minus x plus x squared until plus minus x raised to m minus 1. And if I now do the x multiplication, I get plus x minus x squared plus x cube, something like this. And then I get minus plus x raised to m minus 1, and then at the end plus minus x raised to m minus 1, and then at the end x raised to m, right? Yeah. Yeah, here I had x raised, this is minus plus x raised to m minus 2 I had. Yeah. So if I do the all, see, minus x cancel plus x, minus x square plus x square, something like this, everything will go cancel up, and then I'll end up with 1 plus minus x raised to m, right? But what is this 1 plus x raised to m? You know x raised to m is 0, right? This is 1 plus 0, which is 1. So I found an element v such that 1 plus x times v is 1, which implies 1 plus x is a unit. Okay, I hope you understand this. By the way, when we, yeah, let's, do you have any doubt in this question? Okay. Um, we just now found all the nilpotent elements in Z upon NZ, right? We gave a characterization when if an element belongs to integer is a nilpotent element of Z upon NZ, right? So can we determine all the nilpotent elements in, let's say, Z72 or something? Determine all nilpotent elements in Z upon, let's say, 72Z. So here my n is 72. If I write in the prime factorization, I get 2 times 36, which is uh, 2 times 2 cross 3 squared, which is 2 cube times 3 squared, right? So what are the choices? If A is nilpotent, then we know A is some 2 power I, 3 power j, and then some natural number n, right? Where I belongs to 1, 2, 3, j belongs to 1, 2. Yeah, they both cannot be 0 because each prime divisor of n should divide A. That's all. These are the all nilpotent elements. I mean, you take 6, all multiples of 6, which I mean from 0 to 0 to 71, all are there. 1 to 72 actually. 1 to 72, all are there, and you can find all the nilpotent elements using this technique. Okay, in G upon NZ. Okay, is there any doubt? Okay, so if no doubt, we can go further. Okay, now the next thing is a Boolean ring. Okay, a ring R is called as a Boolean ring. A commutative ring, or sorry. A ring with unity is called Boolean ring if A squared equals to A for any element A in R. Okay, so just give me 1 minute. Yeah, so this is your Boolean ring. So can you give? The question is, prove that every Boolean ring is commutative. Okay, how do we prove this? So commutative means you have to show that for any x and y, product, I mean xy has to be same as yx, right? Okay. Does anyone has any idea how to show this? If every Boolean ring is commutative? So what I have is xy squared, which is xy times xy is same as xy, right? Okay. 1 upon yx squared is yxy X is yx. Mhm. So you consider this equation, and if I mean, consider yx is given as yx, right? So if I multiply x this side and y the other side, I get xy, 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 right? But what is this? Xy, xy is? Um, didn't get anything. Okay. Okay, and do you have any idea how to show this? You can give me hints. Hmm. Basically, this is also xy. Hmm. Okay, maybe I'm not able to get it right now. We'll see this question later. So the next question. The next question is if okay, what do you have to show? Uh, any Boolean ring. Consider let R be a Boolean ring such that cardinality. I mean, with number of elements in R is is strictly greater than 2, let's say, then show that R is not an integral domain. Okay, so basically the only integral domain which is a Boolean ring is Z2. Okay, it has to be a ring with two elements only. Okay, so how to show this? So since there since there are more than two elements in R, and you know the two elements 0, which is the additive identity, and 1, which is the multiplicative identity, right? Both two elements has to be there. So since the cardinality is greater than 2, there exists an element A in R such that A is non-zero and A is not 1, right? Not the additive identity, not the multiplicative identity. So now consider the product A times 1 minus A. What do you get? See, this is not 0. This is also non-zero, right? Because A is non-zero and A minus 1 is non-zero. So, but if you multiply, you get A minus A squared, right? But what is A squared? A squared is A, since you are in a Boolean ring. So this is 0, right? So that means you have a non-zero element and another non-zero element whose product are 0. That means A is a zero divisor, right? So any Boolean ring with more than two elements is not an integral domain. Okay, and of course, a ring with two elements is an integral domain. So, can you give an example of an infinite Boolean ring? Yes, can anyone think of a ring which is a Boolean ring and infinite? Have you heard about the power set of natural numbers? See, now I will maybe if you have attended my another session, there are two TA sessions in a week. One by my colleague Sayed, and other is mine. So if you have attended that session, he has he given a ring which is power set of natural numbers, right? He defined the addition as symmetric difference and the multiplication as the intersection. Okay, maybe I'll just give a recall. Okay, take R to be power set of natural number. Okay, which is set of all subsets. And define the addition as any subset A symmetric difference B is you get A union B minus A intersection B. Okay. Another way to define is some people define in this way A minus B union B minus A. That's the same thing. Okay. So maybe you can take this as an exercise. Find. Okay. I also have to do multiplication and multiplication operation is the set intersection. That is A dot B is simply A intersection B, right? So exercise, find the additive and multiplicative identity. Okay. So what is special about this this ring? You can see it is a Boolean ring, right? For any A belongs to R, what happens if you do A squared? A squared is simply A multiplication with A, right? And here the multiplication is defined as intersection. So intersection A is A. So for any element A, squared is itself. That means it is a Boolean ring. Uh, just give me a minute. There's some problem it seems for recording. 1 minute. There's a technical issue.